Welcome. In this video, I'm going to teach you how to use Newton's law of cooling to find uh, the final temperature of a metal. So let's say we have a metal that I'm not going to give you a name of the metal, but you can say a metal. A metal is placed in a furnace, and the initial temperature and the core temperature, metal core temperature in Fahrenheit is equal to, inside the furnace, is equal to 2000 Fahrenheit. And then at 20 minutes out is equal to 1500 degrees Fahrenheit. And then we know that the room temperature, so we could say room temperature Fahrenheit is equal to 70 degrees Fahrenheit. These parameters may or may not be what you expect around a furnace or inside a furnace for a metal, but what I wanted to show you is the Newton's law of cooling, how to develop a model and come up with the answer. So the answer that I want to get, the question that I have and the answer I want to get is what will be, how long, or basically how long after the furnace, after out, is equal to 80 degrees Fahrenheit. So we need to find T in minutes. Okay. So Newton's law of cooling states is as follows. So you have dy dt is equal to, Newton's law of cooling says that the final temperature, the final temperature is proportionally related to the is proportionally related to the is proportionally related to y and minus the room temperature, which is 70 degrees Fahrenheit for this particular example, where y is the final temperature. Alright, so what we're gonna do to find the model, we need to use something called separable variables from differential equations, from calculus and differential equations. Separable variables. So what that says is that we need to isolate y and t, one on each side, and then take the integral, the antiderivative. Okay, so now what we're gonna do, we're gonna divide like as follows. So dy over y minus 70 equal to k dt. Now we take the integral on both sides. When we take the integral, we get ln, or absolute value, of y minus 70 equal to k t plus c. we're only here. We will get another on the left side. We will get another constant of integration, but we only need to keep one. We don't need to keep two because we can combine the left side and the right side constant into one, and we call it C. Remember, the final temperature is 80 degrees Fahrenheit. That means that this quantity is always going to be, for our model, is always going to be 80 is greater than 70. The temperature that varies from the 1500 down to 80 is always going to be greater than 70. Down to 70 is always going to be greater than 70. Down to 80 is always going to be greater than 70. So what that tells me is that we can get rid of these absolute values. So we're going to have ln, then regular parentheses of y minus 70 equal to kt plus c. Now, we want to get rid of this log. So what do? We take the log on both sides. So log on both sides. So on the left side, taking the log, we drop down the log and we get y minus 70 equal to e kt plus c. And then we put y, move the 70, so that will be 70 plus e, and then I want to take off that c because this is plus, we can take it out by doing a product, e to the c, e to the kt, and then because this would be our constant, we can turn this into a constant. So what basically we want to get rid of that e. So the way we do it is as follows. We take y is equal to 70 plus e to the c, we just call it c, because remember we only want to keep one constant. So e to the k t. So this will be our final model, general model for this example. So now to find the answer to our question, we need to plug in, we need to mess around with our initial parameters. So first, we're gonna find C. We know that the initial temperature, the core temperature of the metal, it's 2000 degrees Fahrenheit. So that's at time t equals 0. When we just took it out, basically right before we just took it out. So that would be, so at t equals 0, our core temperature is gonna be 2000 degrees Fahrenheit. So we plug it in here. So 2000 is equal to 70 70 plus c e to the k times 0. And this becomes 1. So C is equal to 2000 minus 70, and that's equal to 1930. So now we found C. So we plug it in. So y is equal to 70 plus 1930 e to the kt. Now we need to find k. K, we're going to use our second condition, that after 20 minutes out of the furnace, its core temperature is 1500 degrees Fahrenheit. So 1500 is equal to 70 plus 1930 E 20 minutes times K. Of course, we do the math. 1500 minus 70, that's going to be equal to 1430 equal to 1930 E 20 K. We divide by 1930, and that tells me that K, when you do the math, take the log of both sides and do the math, you're going to get a K equal to negative 0.01499. For these cancels here. How did I get that K? You can solve it in the calculator, or you can just do the log on both sides. So that's going to be equal to K. So 20K is equal to ln of 1430 minus 1430, yes, divided by 1930. Divide by 20, divide by 20. So this cancel and K is equal to this. Do it on the calculator, you get that. So now this would be our particular solution. So particular solution for this example is going to be equal to y equal to 670 plus 1930 e to the minus 0.01499 times t. So this is our particular solution. So if I want to find out how many minutes pass for the metal core temperature to be 80 degrees, all I need to do is plug in 80 for y. So 80 equal to that, which is 70 plus 1930 e to the minus 0.01499. And then after you do the math, you're gonna get, which is taking the log on both sides like we've been doing. So T is equal to approximately 351.08 minutes. So after 351.08 minutes, the core temperature is 80 degrees Fahrenheit. So this will be your general solution, and this is your particular. Particular means that you found C and K. You have a particular, you have a specific parameters plugging into the general equation given the initial conditions. Thank you very much. Don't forget to subscribe, please.